So this advanced higher chemistry video is Unit 1, Inorganic Chemistry, and we're going to be looking at atomic orbitals. And orbitals is what's going to replace our language about energy shells. So when we looked at absorption and emission spectroscopy, we saw that that was evidence for the existence of quantized energy levels. That even on atoms that only had one electron, we had multiple lines because these different energy levels around the atom existed and electrons could move between the different energy levels. Now these energy levels, when they were investigated in more detail, it revealed that the model that had been used of just these rings representing electron shells were actually more complicated than the original model had predicted. In fact, each energy level can be subdivided into things called sublevels or subshells, which are scientifically known as orbitals. And these orbitals can have different shapes, which actually leads to slightly different patterns and strengths of lines in the absorption and emission spectrum. The specific definition of an orbital, which is not on the course, but I'm just including it for information, is that an orbital is a volume of space in which there is a greater than 90% probability of finding an electron. The reason we're talking about probabilities is because within orbitals, we're not considering electrons as particles, we're considering them as wave and particles, that wave-particle duality, and when they are waves, it's very hard to specifically locate them, so we can only talk about probabilities. Now here is a diagram illustrating the majority of the orbitals that are found in atoms. There actually are more, but we don't need to know anything about those. Now they've been organized into a hierarchy, into what looks like a pyramid there, and I've shown that the red, yellow and blue ones are the ones you need to know. The ones at the bottom, the green ones, you do not need to know. Now the ones at the top are known as s orbitals. The s orbitals are spherical in shape, and these are the ones that look the most like your traditional electron shell diagram, where you could draw them as rings around the nucleus. And as the energy level increases, the size of the ring gets bigger. The next ones are known as p orbitals, and they are peanut shaped, so they've got two lobes. When it comes to these, there are always 3 p orbitals, and the p orbitals all point in different directions, but they are all the exact same shape. Our next layer down, the blue ones, are our d orbitals. The d orbitals, if you look across that row, 4 of them exist in a sort of cross-shaped, as though they're like 2 p orbitals put at right angles to one another. However, right in the middle, we've got one d orbital that's completely different shape. It is a peanut shape with a donut around the middle. So the d orbitals are not all the same shape. Then we have our f orbitals, which you can see get even more complicated, but luckily we do not need to know these. So we've got our s, our p, and our d orbitals, where we're going to need to know the shape, and we're going to need shape or shapes, and we're going to need to know how many there are of each type. So the first one are our s orbitals. The s is not for spherical. The s is actually for the word sharp, because the s orbitals in electron emission and absorption spectroscopy give sharp lines. But they're spherical, so you can remember s for sphere if you want to. As you go and increase the energy level, the sphere gets bigger. So the 1s orbital, 1 is the first energy shell, is going to be smaller than the 2s, which is the second energy level, and the 3s is going to be even bigger. The next ones are our p orbitals. Now p stands for principal lines, because these are the ones that are most used for identifying particular atoms in the absorption and emission spectroscopy. and they're peanut shaped, so you can remember P for peanut. There's always 3 p orbitals. And how they differ from one another is not in shape, but just in orientation. So if you look at the diagrams, they've been carefully drawn so that you can see 1 p orbital points along the x-axis, 1 points along the y-axis, and 1 points along the z-axis. They are all perpendicular to one another. Next, we're going to look at our d orbitals. D stands for diffuse because D gives diffuse lines when you look at the absorption and emission spectroscopy. Each of the orbitals has a different shape. 4 of them are cross-shaped, but we've got that one that you can see in the bottom right-hand corner of the diagram is a peanut with a donut around it. I use the letter D to remember that they've got one which has got a donut around it. They are mainly only involved when we're talking about transition metals, which is the whole topic of Unit 1, so you will get to know the d orbitals particularly well. They can be split into 2 groups. We have got the ones at the top, and those crosses all point between the axes. So if you look at the one at the top left-hand side, you can see it points between the z and the y-axis. And then the other 2 point between the z and the x-axis, and the other one between the x and the y-axis. Whereas the 2 at the bottom, what separates those from the ones in the top is that they point directly along the axes. This is important because it comes into play when transition metals bond, and the ones that point along the axis are going to react differently than the ones that point between the axes. So to conclude, each energy level can contain several types of orbital. Each orbital can contain only 2 electrons. So one s orbital can contain 2 electrons. Each p orbital can only contain 2 electrons, but because there are 3 p orbitals, that's 6 electrons can be held within all of the p orbitals, and the d electrons, 2 electrons in each d orbital, but because there are 5 d orbitals, that hold 10 electrons. Each electron possesses a fixed amount of energy known as a quanta. And we are going to, in the next video, look at quantum numbers, which are used to describe each electron specifically, telling you the size, shape, orientation of the orbitals that the electrons are found in, and also some information about how the electrons are moving within the orbital. So that's been our introduction to molecular orbitals. The next video is going to talk about quantum numbers.